Welcome to Practicing First Principles Differentiation. Gee, that sounds complicated, but you know it's not. I hope you remember the work here because this is doing some practice. So let's come over here, up to the top of the screen here. You remember that, what we're trying to do, and that is we said that if you want the instantaneous rate of change of a function at a particular point A on a curve, then we have to find the slope of the chord and find the value in the limiting position, which is tangency, of the slope of that chord. Okay, so that's the idea, that we bring this point closer and closer to point A, and if we do, that slope of the chord, which is the average rate of change between those points, approaches the slope of the tangent. And that's going to be our definition of the instantaneous rate of change. So you might have to go back to an earlier video there called Introducing Differential Calculus and just check that out. Anyway, come over to the right over here now, to this graph here, and this is the basis of our process of achieving the slope of that tangent. Okay, and you can see here that if you have point B, its y value will be f of x plus h, its x value will be x plus h, and here's the point of interest. The point A, which has x value x and function value f of x. And what we're going to do is we're going to decrease h, bring b down the curve, and see what happens to the expression for the slope of that tangent, okay, as h tends to naught. That's the idea, exactly what we said before, but we're going to do some algebra now, some actual expressions, and see if we can find the derivative of this function. That is the function that will give the slope of the tangent. Okay, so come down the bottom here, and the derivative function, or simply the derivative of a function, is defined as this. So we're going to try and find a function such that when we do this is the slope of the tangent, isn't it? The function value at b minus the function value at a as h tends to naught. Here we are. Is there a limit? Does this gradient expression approach a value? And we're going to call it the derived function, f dash x, or in Leibniz notation, dy by dx. Okay, do you remember that stuff? Well, what's this right in the middle of the screen? Can you find that derivative function for more complicated functions? You've done some from the textbook already, but the aim of this video is to give you a chance to practice some slightly harder ones and to actually see if you can work one out that you've not seen before. That's a fair challenge, isn't it? Okay, so just remember now, down here, this line, you must start every question with that definition, because we're saying from first principles. Later on, we're going to be able to find these derivatives or derived functions, the functions that give the slope of the tangent to the curve or the instantaneous rate of change. We're going to do it with rules. We're going to see if we can develop some rules rather than go back and do this first principles method every time. Okay, so come on down. I'm going to give you a chance to practice now. And there's a problem for a start, which is worked out. This is from Hayes and Harris textbook there. Just a little clipping of an example they gave, which is very good. You should have that textbook handy by. So here's the definition, always starting with the definition. Okay, now what do we do? Well, for our particular function, we want to substitute in x squared. So this statement here says put x plus h instead of x in the function, doesn't it, that notation? So that's what we're going to do. The function is x squared, so now it becomes x plus h all squared. Take x squared. Sometimes we'll want to put a bracket around this as the function gets more difficult. So just check that the use of a bracket here could be important as the function gets more complicated. Okay, so let's work this out now. We've got h in the bottom line and h is tending to naught. So square the first term. Remember this, expansion of a perfect square. Let's write it down over here. This goes back to middle school maths. Is the first one squared plus twice the product plus the second one squared. Okay, so can we do it here? Twice the product is 2hx plus h squared. and then minus x squared. You can see here we can cancel those out. X squared minus x squared is just 0 there. And then we've got 2hx plus h squared on h. And in one step there we could factorise that. H outside of 2x plus h. You check that with expansion. Yes, that works out over h. Now you know the problem with this limit, finding this limit, is that normally we can just sub h as naught in. In this particular function, the h in the denominator won't allow us to do that, because if we subbed h equals naught in, then it would be undefined. You can't divide by 0. So we need to do this cancelling step. So remember at this stage in harder functions, h is the problem. We need to simplify the top line so that we remove some way that h. H is the problem. So if you ever get stuck, think, how can I cancel that h? So we're cancelling it. And now we have a function here, 2x plus h, whose limit will be calculable. And we could put h as naught in here, and we get the function 2x. Okay, so the idea here is in this move down this solution, we are trying to find the limit of this function, which is undefined at h is naught. So we're going to find an equivalent function which is defined at h is equal to naught, and then find that limit of that equal function, if you like. Okay, we must put this, I like PV, provided h is not equal to naught, after the division step here. Because what we're saying is, as long as h isn't equal to naught, these functions are equal. Okay, but you can't, we want to make some comment about this. Technically in maths, we cannot divide top and bottom by something which is 0. Can't divide by 0. So we need to make some comment. So you must have this step in when you have cancelled. And what does this mean? Let's just check this now. It means if you have the graph of x squared, let's go back up to the beginning. We said we have the function f of x equals x squared. And if we drew a tangent to that, the slope of that tangent would be given by this function, f dash x equals 2x. Can you see how powerful that is? So that at x is equal to 2, on the x-axis, the slope would be, of that tangent, would be 4. And if we're over at -3 over here, then the slope would be -6. This is pretty powerful stuff, isn't it? And I think you can see where it's going. We're going to develop some rules for functions, patterns that they might follow with their derivative functions later on. At the moment, we're doing it from first principles. All right, are you ready? Perhaps study this example again and check that you know what is going on there. All right, come down and I'm going to give you a chance now. Here we are. Here's the question, burning question, red hot question. Are you ready to test yourself? Okay, let's try some. I've got just a few here, half a dozen for you to try. And what we're going to do now is what I want you to do is to treat it more or less like a test. Try the first one and check it. Move on to the next one and so on through the video, pausing it so you can have a look at it. And then I want you to stop, check your work, and then roll the video, because I'm going to go through and do them all so that you can mark them as if it's a sort of mini test and so on. The most important thing is don't just roll the video through and wait to see me do it. Okay, that's very important that you have a go, check your work, and do it like a mini test. Okay, are you ready? Right, here we go. Let's have a look now. All of these questions are the same. Find the derivative from first principle for the following functions. So I want you to pause the presentation now, and it's worth 4 marks down the bottom. See this here? Pause the presentation and I want you to have a go. Remember, always starting with the fundamental definition, f dash x equals limit as h tends to naught of fx plus h. Take f of x on h. Okay, away you go. All right, let's move to the next one. And this one's worth 5 marks. So in SACE, it's basically 1.2 minutes a mark. So you should be able to do this in about 6 minutes. Okay, pause it and have a go. Okay, let's look at the next one. Again, 5 marks. Pause it and have a go. And the next one here, again, 5 marks. Pause it. Okay, away we go. The next one. There we have it. Just remember, hints here, use a bracket for that second term for f of x. And have a look at this one. Now, this is a fairly challenging one, and I've allowed 6 marks here. Okay, because this has got a hint, so you need to pause it and have a go at that and see if you can make sense of it. All right, are you ready? We're going to go and have a look at the answers now. So you can watch me do the questions as we go back to the beginning here and mark your work. Okay, here's our first question. F of x equals x squared plus 1. So we'll start with the definition. Here we go. F dash x is the limit as h tends to naught of f of x plus h. Take f of x on h. You don't actually get a mark for that, but you do lose a mark if that's not there. Okay, so here we go. Let's have a look. The limit, and it must be set out this way every time, of x plus h all squared plus 1. Remember, this notation means everywhere in the function you put x plus h. So in that spot there, you've got to put x plus h. Take f of x. Now look out for this one. I told you about brackets because this is important. He's taking away 2 terms here for f of x. So you need that bracket because it's going to be important in this next line. Let's have a look. Limit as h tends to naught. Oh, now this is a square, so you should be getting good at these now. Okay, quite a common question. Plus 1. Now we're going to take away all of this. Take x squared and take 1. Did you get it? It's very important that when you're taking away that second term, you take the 1 as well. So it's a limit as h tends to naught. Let's have a look now. The x squareds disappear. 1 take 1. And I guess you would have spotted that you needed to have both of those disappear because you need, what do you need? A common factor in the top line of h so that we will be able to cancel the h and evaluate the limit later on down here. So let's factorize it, 2x plus h and over h. So if you're thinking, you know all of these have got to disappear because you can't take out an h factor. Do you get it? See, we want to do that, don't we? With the proviso h is not equal to naught. So this is the limit then of what's left, which is 2x plus h as h tends to naught, which is, as h tends to naught, this will tend to 2x. It's the same function for our derivative, or our slope of the tangent giving function, as x squared was. So, well, does that make sense? Well, yeah, x squared plus 1 is just a translation of x squared, isn't it? X squared plus 1. Why was that? So the slope there would be the same at x is 2 and so on. Do you get it? That's interesting, isn't it? Why are they the same? Think about that one. Okay, let's mark it now. We've got 4 marks. So down the side, I'm going to put the ticks where you have a mark. So there's 1 mark for that line. Now, there's 1 mark here for getting this in here. So somewhere between those two. There's 1 mark there to get to that line, and 1 mark for the cancelling, but it must have this as well, and then 1 for the answer. So there are the 4 marks. And it should take you about 4 lots of 1.2, about 4.8 minutes, about 5 minutes. That'll give you an idea of whether you're working up to pace. Okay, mark your work. Have a look at what we assign marks for. And it's important, though, too, I haven't mentioned, these limits must be there on every line, okay, because that's what we're looking at, trying to find the limit as one point approaches the other along the curve of the gradient of the chord. Okay, as it goes to tangent C. Just remember that now. Okay, come down. How did you go with this one? This was worth 5 marks. You'll see why in a minute. It's a little bit harder. So I'll come over here and start the definition again. Limit as h tends to 0 of f of x plus h, take f of x on h. So this is a limit as h tends to 0. Now let's put x plus h in place of x up here. So I've got to cube it, plus 2x, take away, watch it now, all of this, f of x, okay, all over h. Let's have a look. Now you know why you might have done binomial expansions. Here's one here, the cube. I think in this one it's easiest to use Pascal's triangle to get the coefficients rather than combinations, go straight to the numbers. So we've got highest term x cubed, one of those, plus 3x squared h. Remember the pattern in the binomial? Decrease the power of x by 1, increase the power of h. So this is 3x h squared and 1 lot of h cubed. Okay, take up plus 2x, take x cubed, take 2x. So just check the binomial expansion in there. Here it is here, the 4 terms, and the number of each term, the coefficient of terms, comes from the Pascal's triangle. Okay, so this is a challenge in maths. We've moved on to a different area, but we still need to remember the principles that we've learnt before. So let's have a look now. X cubed disappears here. 2x, take 2x. All the terms left here have got h in them. Let's write them down now. You could leave this line out, but we'll put it in here because for completeness here. Okay, let's now factorize it. We know we are looking at removing the h so that we can evaluate the limit. So here we go. So we've taken out a common factor out of each of those terms and dividing by h with the proviso at that stage that h is not equal to 0. So it's going to be equal to the limit of the function which is defined at that point. So it's this thing here. And what happens to that function as h tends to 0? Well, 3x times 0 and 0 squared will be 0. So the answer is 3x squared. So that's our derived function, or our derivative. Now I've allowed 5 marks for that. Can you see why? Well, first of all, there's one for that. Now I want to give you a mark for this one as well, for the binomial. That's a bit generous. Usually it's only about 4 marks. But let's be generous today. Okay, and then one for this line. We're going to give you one for the cancelling. Must have this there, and then 1 for the answer. So we'll give 5 for that one. All right, are you getting some marks? I hope you're enjoying this. And of course, you can go back and check out what I've done again and the reasons for doing it. That's important. Okay, come on down now to this one, the reciprocal function now, 3 on x. So let's have a look at this and go through the same process. Nice setting out here from the basic definition, and that's why it's called first principles. So we always start with that statement over h. And so let's have a look now at f of x plus h, putting in place of x in the function x plus h. So we've got this, take 3 over x. Won't use a bracket here now because there's only one term in that function. So here we go, h tends to 0. Oh, what are we going to do here? This is interesting because we've got to simplify this. Do you remember your work? Common denominator in the top line there. And so it's going to be, we've multiplied that by x, we must multiply the numerator by x. We multiply this by x plus 1, we must multiply the numerator by, x plus h, must multiply the numerator by x plus h. And it's all over h. Wow, that's hard. Let's give you a mark for that. Okay, now let's have a look at this. What do you do next? This often confuses people. And why is that? Well, let's have a look. Because you have a denominator there in that fraction and one here. Let's look at how you might think about that. If you were saying 3/4 divided by 2, you could say that's half of 3/4, couldn't you? So what would you do? It's a half times, of is times in maths, isn't it? A half times 3/4, which is 3 over 2 times 4. Does that help? What does that mean over here? Let's see what that means. It means, if we do this top line, 3x, take 3x, take 3h. Now the bottom of that fraction can come down and live down here with the h. Can you see that? And the way you want to think of that is go back to simple numbers, because that's all this expression is going to end up, isn't it, when we evaluate it, removing the pronumerals, or the letters standing for numbers. We're going to get something like this over here. And see what happens? Those two end up being a denominator together. That product is going to be a denominator. Okay, so that's the way you might think about that. Keep it nice and simple. And logical. Maths is, of course, very logical. So here, 3x take 3x, and it's got neg 3h in the top line. Is it going to work? Oh, yes. We're going to be able to cancel out the h and evaluate the limit. There it is. There's the step we want, provided that h is not equal to 0. And then we've got the one that we can evaluate now once that zero's out of the bottom line. It's neg 3 over x by x plus h. So we can evaluate that. Substituting h is 0, we get neg 3 over x squared. That's an interesting one. Okay. Actually, you should have done some of these denominator ones already, these reciprocal functions. But if you haven't, here you are, study this. Okay, let's go back. Correct substitution in there is worth 1. Common denominator there is worth 1. And then simplifying it to here, another 1. And then coming to this line 1 and evaluation, your final answer is 1. So that gives you a total of 5 there. Okay, so check it out. How are you going? Getting a few marks, I hope. Let's go on to the next one now. Here we are, 1 over x plus 2. So we're going to have the same sort of challenge there because you have that reciprocal function, you have a denominator. Okay, start off in exactly the same way. Okay, neatly putting down the limits here, limit expression, because this is, well, from first principles, from a definition, if you like. And it's important to show the fundamental maths that's going on here. Okay, so here we go, x plus h will be 1 over x plus h plus 2. remembering what f of x plus h means, it means replace that x by x plus h. Now we're going to take 1 over x plus 2 and we're going to divide by h. So it's a little bit more unwieldy looking, this one. Let's have a look. Common denominator in the top line would be the product of the two denominators. Okay, like that. And then we would have, this has been times by x plus 2, multiply its numerator by x plus 2. Take, let's use a bracket, this has been multiplied by x plus h plus 2, we must multiply its numerator by x plus h plus 2. Now these are biggies. And then we're going to divide by h down there. So let's check it out. It's a limit as h tends to 0. Let's expand that top line, x plus 2. Now, why have I used a bracket? Look at that negative. Negative x, take h, take 2. And let's do our denominators here. They'll go down and join h in the bottom line. For that reason we looked at last time. So that's important. Okay, now you would know you had that wrong if you didn't put that negative right through every term here, wouldn't you? Because you wouldn't be able to cancel the x's and the 2's, and then you would not have a h factor to cancel the denominator out, and you know you need to do that. So this is neg h over h by x plus h plus 2 by x plus 2. Okay, so cancelling here with a proviso that h is not equal to 0. And then let's go on. We're getting there. That was the important step. Okay, so this is neg 1 over all of this. Okay, and we've done it. There's no h in the bottom line by itself to stop our evaluation, if you like. So it's a limit as h tends to 0. Now let's stick, well, we don't need that. Let's just stick 0 into the function. So I'll go back and get rid of that. So if I put 0 here, then we've got neg 1 over x plus 2 by x plus 2. Okay, so that becomes neg, what, 1 over x plus 2 squared, you want to call it that, or neg x plus 2 to the neg 2. Either of those would do as our derivative. Let's go back. There's 1 here, certainly 1 for all of that, that's hard, got to check that, and 1 here, and 1 for this function and 1 for the evaluation. So again, there's 5 marks I'm giving you for that. Fairly generous marking. It's usually, as I said before, only about 4 marks. Okay, how did you go? Check it out, because you can go back over this video and see what's happening there every time. So let's come down. Oh, this is getting a bit hard, isn't it? Well, we've got a lot happening here. Okay. Don't be daunted. Let's just go on with the process. So f dashed x is the limit as h tends to 0 of f of x plus h. Take f of x over h. Okay, here we go. Careful work here. And you know it'll come out. So it's 2 plus 1 over x plus h take 3, take bracket now, 2 plus 1 over x take 3. So you can see why we're needing a bracket here, can't you? When there are 2 terms in the function expression and we've got to subtract both of them. So let's have a look now. Limit as h tends to 0 of 2 plus 1 over x plus h take 3, take 2, take 1 over x take 3 all over h. Well, we can start to do our simplifying here. Just look at that sign. Remember, I took each of these away, And now we remove the 2. So can we get a common denominator between these two? Let's do that all in one step. So hang on, I'll just go down a bit lower here. Okay, so here I'd have x take 3 take x plus h take 3 all over x plus h take 3 by x take 3. That's that common denominator step again. I'm just doing these circled terms here over a common denominator. So check that, and then we've got the limit as h tends to 0. Now let's try to remove this bracket here. So it's x take 3, take x, take h, and take neg 3 is plus 3. And let's combine the denominators as we did before. So there's h in the bottom line, and the other 2 come down to join it, if you like. So now let's have a look. It's all working, isn't it? Isn't it beautiful stuff? All disappearing. So I've got the limit as h tends to 0 of, here we've got neg h over h, x plus h take 3, check it by x take 3. You've got to be careful here. So if you cancel, we've got our next almost final line now, limit as h tends to 0 of neg 1 over all of this. You don't need this many steps, you can leave part of that out. So you should have the proviso, h is not equal to 0, and subbing h is 0 into this, you can see you get neg 1 over x plus 3 squared, excuse me, and equals, if you like, neg x plus 3 to the neg 2, either of those two. Let's mark it. Okay, so up here, 1, I think I'm going for 1 here, 3, showing that, cancelling 4, and 1 for the answer 5, something like that. You're getting the idea? You must show the working out, because if you get the wrong answer, you still get these part marks. So that's important. So let's go down and have a look at your big challenge question. And were you able to do it? Let's just bring down the challenge again. Hint. Okay, let's have a look at the function for a start, so that we can see where the hint is going on there, what that means. Now, generally, you don't get hints, and the reason I've given you one here is that technically this function is not in the course at this year level. You are expected to be able to do it later on. So what does it come to? It's root of x, so it's a root of x plus h. Take the root of x over h. Okay, so if you have the limit as h tends to 0 of this thing. Ooh, now, is this hint important up here now? Use the multiplication of top and bottom by the conjugate to obtain a function. Top and bottom of this expression. Do you remember the conjugate? And you don't want root x plus h up the top. So the conjugate in thirds means the term with the opposite sign between it. And do you remember it all? So why we do that and what happens when we do that? Well, have a look here. We must multiply top and bottom by the same thing so that we keep the meaning of the fraction the same. So it's equivalent to multiplying by 1. Now, what happens when you have a product a plus b by a take b, or the other way around here? It's the first one squared minus the second one squared. So we have deliberately used our prior knowledge of expansions so that when we multiply this top line out here now, we will get that pattern, and because we're squaring both terms, we will remove the square roots and hopefully what? Be able to cancel by h. So it's fairly logical. Well, it's very logical. Fairly easy to see, isn't it? Let's look at this pair of terms here. That by its conjugate is the first one squared, which removes the root over x plus h, minus the second one squared over, down with the denominator now, we have the conjugate of that expression. Okay, and here we go. Can we cancel h all together as well? Goes in that once and to that once. So we have limit as h tends to naught of 1 over root x plus h plus root x. Oh, it worked, didn't it? With this important piece of mathematics here. I don't think you'd ever would have thought when you did that in middle school that it would be so useful in differential calculus later on. So I don't think we need a limit now, do we? We'll just put in h is naught, so it's 1 over, this would be h is naught, so that would be root x plus root x, or 1 over 2 root x. Or you could put it as a half x to the neg a half, something like that. Okay, so there we have it. So that was a challenging one because you wouldn't have seen that one before. So there's 1 mark there, 1 mark for this, 3, and I think I'll give you here 4, I'll give you 6, 5 and 6, okay. And I forgot to put in, look out, I nearly lost a mark. What's this? I forgot that. Okay. So I think I allowed 6 marks for that. So it's a bit generous there, but I wanted to encourage you on that hard one. So how did you go? Did you get a few marks? I think overall there were 25 marks. So go back and study it, and just be careful with the algebra, little tricks that you need from the binomial and other things from previous years, and you can do well on this. Okay, so cheers for now. Catch you in a later presentation.